we make deletion optional. The code. That's not because it's hard. It's not that hard, but because if you never programmed before, if you're just learning how to use Python, deletion, as we're gonna talk about in a second, it's a little tricky. But if you program, especially in a language like Java, it shouldn't be that hard.
It's like super easy if you just pick
So today, we have to do something so you can do your homework, right?
it shouldn't be that big of a deal.
We have to do that. So we cannot drag it anymore. We have to do recurrences. But before we do that, we need to tie up a few things. So there was a proof last time. That's an important proof. And we need to discuss a little bit the BSD to make sure everybody's on the same page. Because I was waiting for you guys at office hours, but no one showed up. So because of that, we'll do the BSD. We'll try to do those two things quick so we can do recurrences, so everybody can do their homeworks. So where was that proof? You guys remember this first thing? Let me start in here. There was a chain of ideas that was fairly complex to determine the harmonic series approximation logarithm. That was the last thing we did in class on Tuesday. That has value way beyond the actual proof. To understand how to bound the elementary math, discrete math, logarithms versus discrete series, aka without calculus. That's an important thing that's going to play on as you try to understand the fundamentals of calculus with E, how do you define integrals, so on and so forth. These things are going to become very important. So here's that chain of ideas. If this is the series like this, and the other series was, I think at n plus 1, right? We have that this one is monotonically increasing, and this one is monotonically decreasing. In fact, we put this inequality 1 plus 1 over n at n. It's more than, I'm going to write it like increasing, like I'm going to go up a little bit. 1 plus 1 over n plus 1 at n plus 1. This is an, this is an plus 1. This is smaller than 1 at 1 over n plus 1 of n plus 2. That is b n plus 1. And this is smaller than, so there's no equality here, 1 plus 1 over n plus 1. That is b. Remember this? We're saying that the chain of A's always goes up and the chain of B's always goes down. So they must have a limit, being monotonically increasing or decreasing and bounded. The only way is they asymptotically drive to a value. That value is in the middle here. That value is E. E is the limit of both. This is going to E from under, and that's going to E from the top. So that was idea number one. And then we had a few consequences of this. So let's call this one. That's kind of, we started the proof for this, but we didn't finish it. But then the other stuff I think we proved. Part number 2 was from 1, we want to get 1 over n plus 1 smaller than ln of 1 over n smaller than 1 over n. So this is from 1. This is a very simple thing. We take this inequality, and when we take logarithms, log of e, its natural logarithm, log of e will be 1. This will be n times log of 1 plus 1 over n. Like, so if I take the logarithm, I get ln of e smaller than. This is n ln of 1 plus 1 over n. This is n plus 1 ln of 1 plus 1 over n. There's very few steps to get to here. That's very simple. If I have to define e, which is the limit, and I have to define the natural logarithm, which is the inverse of the exponential function. So I need to define e, then the exponential function, then the logarithm function to be able to do these operations. Now we got to here, and from here we got number 3. What did we do? I don't have the result in here. Was that if we sum those things up, we get something like the h, I think n, the harmonic series, 1 plus 1 over 2 plus 1 over n. It's smaller than ln of n. There's something like that, smaller than h of n plus 1, which obviously bounds the harmonics and logarithms very well together. That's also very easy to see from here to here. The trick in here is to telescope this series, to think of this logarithm as ln of n plus 1 minus ln of n. I don't know how many people remember this from last time. When I start summing up the terms, the left side goes to harmonic, right side goes to harmonic. I think this might be h of n plus 1 minus 1 or something like this. And this stuff in the middle telescopes, meaning everybody is canceling half of it with the previous and half of it with the next. So I'm left with first minus last. That should be in your notes from last time. So this is an important, the way I'm emphasizing this is that it's not just a cool math. It's an important transition from discrete math to calculus. This is exactly where the transition happens. A lot of basic proofs here are discrete proofs, aka induction, combinatorics, you name it. But once you move towards that direction, you start talking about logarithms and integral, and that's all of a sudden how you find yourself in the calculus realm. Now, most of you will not need this exactly how do I define integral, logarithm functions, e, what's the limit, so on and so forth. But just in case you do, this is how it happens. Now, what we started last time is a proof of this. And we said, let's just prove this part. Right, that's how we started. Let's prove this part. This one, presumably, is similar, just the other way. It's decreasing instead of increasing. We need to prove this one is increasing. So here's how we started that proof. So 1 over n at n is smaller than 1 over n plus 1, n plus 1. This is not a trivial thing. Make a note that while the interior of the fraction is going to 1, right? The more n grows, the inside stuff is going to be closer and closer and closer to 1. The exponent is going to infinity. So it's a competing goal here. Who goes faster to the limit? If the base goes faster to 1, then the limit should be 1, right? 1 at something. If this becomes very, very close to 1 quickly, then even though the power goes to infinity, if this guy is quicker to go to 1, the limit might be 1. On the other hand, if the power goes very fast, suppose I put here, n cubed or 2 to the n or something like this, then even though this goes to 1, the exponent goes so much faster that this still goes to infinity. So there's a competing, who goes faster to its limit? Because 1 at infinity is an ill-defined, depends who goes faster there. So that's why this will require some skill here. Let's see where we were last time. We said 1 plus the sum of k equal 1 to n of n factorial, k factorial, n minus k factorial, 1 over n to the k is smaller than 1 plus sum of k equal 1 to n plus 1 factorial, k factorial, n plus 1 minus k factorial, times 1 over n plus 1 of k, plus, that's outside the sum, 1 over n plus 1 at k plus 1, n plus 1. So how did I get this? I applied the binomial theorem, x plus y at power n. These are the coefficients, the binomial coefficients already expanded. 1 over n is this 1 over n here. The 1, which is the x or the y, it's 1 at some power, doesn't exist. This sum would be from k equal, the k equals 0, it's outside. This is the k equals 0. This is the k equals 0. Now this sum will go one more term. We'll go to n plus 1. That is the additional term in here. This one in here is k equal n plus 1. Right. In case you were hoping that you're not going to see the binomials again, that's not true. It's going to show up in your exam, in your final exam. Right? All the problems I'm going to propose for the final exams are going to be combinatorics, okay? So you may be lucky one of them doesn't get in, none of them gets in, but if they do, there will be binomial coefficients, okay? Because everybody else will be on graphs and probabilities and induction, so I'll make sure everybody gets to study binomial coefficients again. They're our friend.
Can I ask you a double question? So, you said a second ago that you're comparing the growth rate of 1 over n inside of that first statement to n. So, can you think of E as the ratio between the growth of the harmonic series and the ratio of the growth of like n plus n? Or like, how can I think of E differently?
There might be a way to think like this, but that's not the conclusion of that thinking. Like if you look at the ratio between the harmonic and logarithm, say that's not E. But if you take some derivatives, you might get to E. So I think that way expressing the integral on the, it's the same principle of if I differentiate logarithm, what do I get? What if I differentiate some function, what function differentiate against logarithm? That's what you want to get with that ratio. Because the differential, if you remember, is defined as a ratio of limits. But that's not, your intention to think like that is correct, but the result is not. What I was pointing out is that this is an interesting thing, and it's not trivial. It's easy to see that it's not easy to see that it goes to some constant like E. It could go to 1, it could go to plus infinity. It could go to other constants, depending how you set this function. It's a competition of whether this goes first to 1, or faster to 1, or this exponent goes faster to infinity. Now back to my proof here. This is a binomial expansion. 1 goes away with 1. This I'm going to think of as bonus. Like I won't deal with that. I need to prove this is smaller than that. If I ignore that and I prove this is smaller than that, clearly adding that small bonus in there will still be good. It's pretty small, that one. So let's try to prove it without. I'm going to move all the sums on this side, k equal 1 to n, and do some common factors here. I won't spend time on those. You'll have to work it out on paper. So what happens here? I move both sums on the left side, right? The sums are k equal 1 to n, k equal 1 to n. So it's k equal 1 to n. I did common factors everything I could between the terms. So between those two terms, n factorial is a common factor. K factorial is a common factor. Is that right? And then n minus k plus 1, this one is a, did I miss an n minus k somewhere? No. So that one is a common factor here, but then I have to figure out what's left. This n to the k is here, the n plus 1 to the k is here. Where is this n plus 1 here from? Why do I have an n plus 1 here? Yes. For n plus 1 factorial, because the common factor was just n factorial. Where is this n minus k plus 1 coming from? Yes. Right, there's a factorial that's been taken out more than what it should have been, the factor, so I have to put it back in this factor, right? If you think of this factorial, you see n minus k plus 1 factorial is here, but not here. All right. So that's what I want. This is want. I don't know how to prove this, but that's what I want. Now, here's a more demanding wish. It's quite wishful thinking there. If this is negative, I'll be done, right? This is a sum of a bunch of terms. Every term is a coefficient times a difference. If all those differences are negative, the whole sum will be negative, right? That's quite a lot to hope for, that all those differences are negative here. But it would work very simpler if all of them would be negative. So what does this mean here? This is n plus 1 by k. So this is 1. I did a little bit of manipulation of terms. And further, I can write this as n plus 1 plus k. All of these are 1. Now, because I'm so good at math, I remember the following inequality from high school. If x is a real number greater than -1, x is real. And n is a natural number, then 1 plus x at k, I guess it's k, not n, it's at least 1 plus kx. Anybody remember this inequality from high school? Yeah, 1. All right. Well, let's see what kind of it means first visually, right? What does it mean? I'm going to plot two functions. Let's call this function f and this function g, f of x and g of x, right? And this g is a linear function here, right? So this is x in here. From x equals 0, how much is f when x is 0? 1. Right here, that's f. And how much is g?
1.
1, both of them here. How about when k equal, let's say x equal 1. So this is x equals 0 here. How about x equal 1? How much is f in x equal 1? 2 to the k. And how much is g? 1 plus k. So I think g being the linear function, they both have to pass through this point. So g is a linear function like this, and f has to be an exponential function like this. So that's f. Now I didn't plot as a dependence on k here, just on x. I could do the same plot for k. What happens if k, let's do the same plot for k with a fixed x. What happens if k is 0? I keep x fixed now. When k is 0, what happens? How much is this? 1. How much is this? 1. They're equal. But when k is 1, what happens? This is 1 plus x. Say it's in here. How much is this? They also equal. So now g is a linear function in k too. It's linear in x or in k if the other one is fixed. That's g. And f in here is x polynomial in k in x, and this in here f exponential in k. So this function, it's like this. That's f. So somebody may say, wait a minute, didn't you say f is greater than g? And look at this, it's under. How does that happen? Isn't that funny? I tell you first f is bigger than g, and then f clearly goes under g. I mean, do we know the exponential functions are curved up? So if it's equal here and here, it gotta go under in here because the exponential are convex function. How does this happen?
It's only in case natural number.
What? Louder?
It's only in case a natural number.
Only when case a natural number. It's equal here and here, but since it's convex, what do we know after that for all cases that happen after? Once it touches the line twice, it has to go up. It will never come down to the line. So that's a very important inequality too, that I encourage you to study for more than just x being -1 and k being a natural number. Now, why do I need x to be bigger than -1? Because the base of this exponential has to be positive. It wouldn't work if the base is negative. So here's my conclusion here. How can I finish this proof? I think I can use that inequality right there. If I put in x equal -1 over n plus 1. How this inequality read in here if I put x that value? I'm going to get 1 plus x, right? That's -1 over n plus 1 at power k is greater than 1. Now this is a k here, minus k divided by n plus 1, right? I'm simply replacing x with this -1 over n plus 1, this inequality. And now I'm looking and I say, is that what I'm looking for in there? That thing that I want in here? Is this thing that I want, this thing in here? N plus 1 minus k divided by n plus 1 is the guy on the right side? How about the guy on the left? N plus 1 minus 1 divided by n plus 1? Is that n plus 1, n divided by n plus 1 at k? This one here is just n divided by n plus 1 at k, and that one there is n plus 1 minus k divided by n plus 1. No? Yes? Maybe? Is that the one there? See, it's good to remember from high school stuff. Yes.
Do I need to, I couldn't do that on the exam. Would I be required to make a creative assembly?
This is not going to happen in the exam. Let's be clear about that. Right? That would be a bummer. It's not for the exam. But there's still one more problem here. I think I convinced you guys that this is a complicated thing, that we finally got to the end of it by remembering high school stuff and figuring out what to plug into it. But there is one more thing. Since I remembered this from high school, I don't know if it's true. Is it true? I wish it's true. I think I can prove this by induction. On k. I fix the x, and I prove by induction on k. What would be my induction step? This is a weak induction problem. What's my induction step here? If it's true for k, it's true for k plus 1. Right? So induction step would be like, if 1 plus x at k, what was the property? It's bigger than 1 plus kx, that is for k, that's p of k. Well, then what happens to k? How do I write this for k plus 1? 1 plus x add power k plus 1 is bigger than 1 plus k plus 1x. And then I need a base case, right? But I think I already done the base cases, right? X equals 0, x equals 1, k equals 0, k equals 1. I think base cases are done. Let's do the proof. How do we start these induction proofs again? We start with a new customer. Who's the new customer here? This guy. 1 plus x at k plus 1. What's the relationship between this new customer and the previous customer? Is the old customer times? It's 1 plus x at k, the old customer, times 1 plus x. Now what do I know about the old customer? Is greater than something. So I can do the induction hypothesis, say 1 plus kx. This in here is the induction hypothesis. Times 1 plus x, which I can open parentheses now. What do I get? 1 plus kx plus x plus kx squared. Everybody sees that? 1. Write it nicer. Kx plus x plus kx squared. 1 plus kx plus x plus kx squared. So this, if I group the term, it's 1 plus k plus 1x. I group the x's together. Plus kx squared. Now what do I know about kx squared? This is definitely, this is the guy I actually want, right? This is 1 plus k plus 1x. And this is positive. Why is that? K is a natural number and x squared is a square. So because this is positive, this is now bigger than 1 plus k plus 1x, and I'm done. That's exactly what I wanted to do. So this is not that bad. This could happen in the quiz next week. Really. Like this is the same induction proof that you've seen for 3 weeks now. It's now with a sum, it's with inequality, but it's not any harder than the ones we've seen with inequalities that were presented in class or the homework. It's a very simple induction step in here. You have to, though, realize that what you want, this inequality could be quite complex if you play with both variables at the same time. But if you keep one of them fixed, like in here x, it's a fixed thing, and you play with the k, or you keep k fixed and you play with the x, it's very easy to understand what's going on. So that proves this proves that proves this, and then he bounds finally the harmonic series to the logarithms, which was our plan from the beginning. So now we know why the harmonic series is roughly the logarithm, and we have beautiful proofs along the way. Nice. Before I move to recurrences, which is what I really want to do today, let's talk a little bit about that BST. That I know some of you didn't ask because you did it, because you told me, and some of you didn't ask because you just didn't get to BSTs yet, I guess. I don't know. I have 2 things that I want to show you. First, let's remember what a BST is. This would be a small discussion just to recap it a little bit. 18. 17. 4. 13. 9. Everybody remembers the idea of a BST? I mean, you still have to work on the how to control the inside the computer, how the tree gets controlled with arrays or pointers. Pointers are easier, but if you don't know them, they're harder to figure out. Arrays are easy to figure out, but it's kind of more messy to do the tree that way. The conceptual property, apart from being binary, every node has 2 branches at most. If it doesn't have a branch, we can put a null in here. Say, like there's nothing on that side. The way to think about this, if this is x is a node handle, like an ID, conceptually I'm going to have x dot value, in this case that's 18, x dot left child, that is this y here, and x dot right child, that is this z, and x dot parent, that is this d, as handles. Conceptually. Now, if I'm in an array, I have to manage this with indexes. If I'm in an object in Java, this would be fields of that object. If I do it in Rocket, those would be, I don't know, recursive functions. Good luck with that. Now, what we didn't talk about and might be tricky is this idea of a successor. I think finding the minimum, it's easy, right? If I usually all these functions start at a point. Say I start in here at this 6. That's my starting point. I could start here, here, anywhere I want. How do I find the minimum? Where is the minimum if I start at a node? Go left as much as possible. What if there's no left? That's the minimum. That's easy, right? Where's the maximum? Right as much as possible if there is a right. If there's no right, you are at the maximum right now. Good. We already talked before about in order. If I start reading everything, left, node, right, I'm reading the whole thing sorted. So recursively speaking, if I start here and I imagine do the left side, then the 15, then the right side, that will be sorted assuming I do the left side in the same way. For the left side, I have to do this left side, then the 6, then the right side. And then this will have to be 2, then 3, then 4. So the in-order reading of a tree, or sometimes called traversal, is to say recursively, when for every node, read the left side with the same procedure, print the node. So read in order will look something like this, of some node x. Read in order on x left child, do that thing from the left side, then print x dot value, right? Print the x value, and then read in order right side. So this recursive procedure would print all the values in sorted order, assuming the tree is valid, because it will do the left side. Everything that's below a value will be printed in the left side, then everything that's after it will be in the right side recursively. I think it takes more time to understand conceptually how this actually works than to implement it. Implement is a piece of cake. Insertion, I think if you do the search, it's easy because you always start in here. How do I look for a value? That's binary search, right? I compare that value with a node. If the value is smaller, I go on the left side. How do I look for, say, I don't know, 14 in here? I compare in here, I go left, right, right. It's exactly binary search. If it's bigger, go to the right. Now I go here and I see the null, right? Because after 13 I go here. What's my conclusion here when I see null? I was looking for 14. If I find null, means 14 is not in the tree. Hands up, who's with me? That's an obvious thing, right? That's binary search. Now what if I want to insert 14? Then insert it whatever I look for it, whatever I ended up looking for it. I mean, if it's another 14, I may have to deal with that problem. But nevertheless, search, once I'm done searching for a value, if I want to insert it, it will be a constant time operation because I'm already in there. It's not like an insertion sort where I have to make space in my array. I'm already where I want to be. The only one that's not discussed is successor. If I give you a node, say this, let's call this not x but some other thing, a, some other handle, this one here. By successor I mean in increasing order the node that has the next immediate value. So that will be who, if this is a 7, who's in reading all those things in order, who will be the next value? The 9. That's the successor. Successor means given a node, what's the node that's the next in the whole tree. Or in a subtree if I start looking at, if I start looking only in this subtree, then I mean in that subtree. Right? So, any idea how to go look for the successor? Just intuition. If I'm here, where should the successor be? To the right side. Clearly it cannot be on the left side. Because on the left side, all values are smaller than it. So left side is out of question. Now, if I go to the right once, should I keep going to the right? No, because this is now a candidate for succession. Everything on the right side of this dude, which is A, this is A dot right. Everything on the right side of this will be bigger than 13, so it's not a candidate for succession. How about the left side of 13? Is that a candidate for succession? Would that be a better successor than 13? Yes. So if I could go to the right, then I should go left, and then left, and then left. Is that a good idea to keep going left? Is that better and better successors? Yes. Because every time you go left, you go closer to the value where you started, but you cannot touch or be below that value. So if there's another 7 here, that may happen, but this is clearly the successor of this 7. So again, if I could go right child, if this exists, then go right, then all the way left. Makes sense what I'm saying? If I could go right at least once, it makes sense to go right and then go down as much as possible on the left side. Yes?
So the only part of the tree that would not have a successor would be the minimum then? And
The
we could
minimum,
say
the
if
minimum,
it's
the maximum doesn't have a successor. The minimum doesn't have a predecessor.
oh, okay.
Because the maximum one is 20, can't go to the right. But there is another place. If there is no right-hand side, that could happen, right? Think about this 4. This 4 doesn't have a right child. But it does have a successor, right? Which is 6. So if not, if there is no way to go to the right, where can I go? To the parent. But to the parent might be going to the parent as I was the right child, or go to the parent as in I was the left child. So in this situation, when I'm looking for successor, does it make sense to go to the left as in my parent's on the left because I was on the right side of my parent? Does that make sense? I mean, let me ask you differently. If I'm the left child and I'm asking for succession, when I go to the parent, I should know whether I'm going towards the right or towards the left. And that can be done with the tree structure, because if I go to my parent, then I ask, am I the right child or the left child of the parent? So I don't need an additional variable to keep track of that. I just ask my parent which child I am. So if I go to the parent, let's start build up like that. So I don't have a right side. We already said the left side is not valid for succession. So for succession, this is NA. And this is no. I go to my parent, and now what do I do here? Is that the successor?
No.
But it could be. What if my parent is on the right? If my parent's on the right, is this automatically the successor?
Yes.
I see heads going both ways. Again, what situation? I mean, I couldn't go to the right. If I could go to the right, that's the one. Now I go to my parent, and I'm asking, is the parent on my right or not? I don't want to answer the question. I want you to ask this question. In fact, I care more about you asking the question, trying to answer it, than the whole problem for it. What happens if I go here? Is this the immediate successor? Can I just go, assuming I know I'm going to the right, I was the left child, right? This is me, X, this is my parent, and X happened to be left child of P. Can I declare immediately P is the successor? How about if P is linked to somebody in here like that? If P is the left child of some dude here, is this a successor to this or not? Yes.
No, because that means that they're pointing at one to the right of that one.
This is in the right subtree of this one here. Being in the right subtree, the value here has to be bigger than the value here. But this is bigger, right? What if this has another, it's linked this way. Is this the better successor than this? Which one out of those two is the immediate successor? Is this or this? This one. How about if there is a child in here? Is this a better successor for X than the parent? No. It looks like if I go to the parent towards the right side, meaning I was the left child, this is the successor. What if, so this is the one we're looking for. What if I was going left to my parent? This is clearly not a successor, right? Why is that? It's smaller. And if this one has a parent this way, this is not a successor either, right? It's smaller. But what happens the first time I go to the right? Is that a successor? So that's kind of the situation. The first time you go to the right, as in a parent ancestry tree, that's what the successor is. So let's recap the thing. You still have to figure it out. I just want to push you a little bit for help. If there is a right subtree, you just go in there, once to the right, all the way to the left. If there is no right subtree, I go to the parent and parent and parent until I go once to the right side. As long as I go to the left side of the parents, I'm not finding the successor. The successor is the first time when I go to the right. As long as I keep going parent, 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 and I'm always going, I'm the right child of that parent, these are not successor. They're all smaller than this value. But the first time I go to the right, that's what the successor is. What happens if I keep going here to the parent and I never go to the right? I have some value here, and I go up, 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 up. There is no, this is null. And I'm trying to find a successor. I go up, 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 but I never end up going to the right. Why?
Because it's the greatest value.
This is the greatest value. That's why it has no successor. Okay. Finally, for people who are ambitious, how the deletion works. So let's do this a little bit more conceptual. I have a tree here, right? This is the node I'm trying to delete. Unfortunately, that one's in the middle of the tree. Obviously, if I'm trying to delete something that's not in the middle of the tree, that's easy. Like if I try to delete something that only has branches some way, right? Here's a tree, a node here that has only a left child. Every time I try to delete a node like this that has only one child, it's very easy. Just promote the child in its spot. Do we all agree that if this is a binary search tree, I'm trying to delete a node that has a left child but no right child, or a right child but no left child? All I have to do is get rid of that one and promote this one here. The difficulty is that I'm trying to delete something that has left and right child. If I get rid of this, now what? I can't really link this stuff in here. Remember, I have to preserve the property, smallest values on the left, bigger values on the right. So what will do? Yes?
Well, there's an easy way to do it that's not very efficient. Now what you would do is that you would get the leftmost value for the entire tree over and over and over. Put that in an
Rebuild
array
the whole
list.
tree.
Rebuild it as an array list, remove
Right.
that element,
Right.
and then rebuild the tree.
So start from scratch. I really don't like that one, right? Because it says delete the value, pretend you don't have it, rebuild the whole tree. I'm looking for something more like I want to keep as much as I can in place, not rebuild the whole thing. Yes.
Find the successor.
So what is the successor of this guy here?
Go
First
right.
of all, he must have a right subtree, right? Because if he wouldn't have a right subtree, I wouldn't worry about it. I will just put the left subtree instead of it, and I'm done. I find the successor. Where is it? Again?
Right, left, left.
Left, left, left. That's the successor right here.
Swap values with the successor.
Before we do that, can the successor have kids?
Yes.
Which side? both sides?
Right.
Can have a right kid, the successor? And this guy can have an entire tree under it. But can the successor have left kids? Why not? Because he wouldn't be the successor. So we know for sure the successor doesn't have left kids. And then what do?
We swap the values of the successor.
We delete this one here.
Yeah.
We put the successor in here, and now we're in the same kind of situation where, or you say swapping, okay.
Swap. And then you.
So then I swap this with this, and what he's hiding here is that by swapping these two guys, it's still a BST. The values that were on the left, smaller than something, but on the right, check that out. This, by swapping this with this, it's still a valid binary search tree. Everything on this right and everything on that right will check out, magic. But then what do? And now I have to delete this one here, right? Because I swapped them, but this one is something I don't want to delete now, but this one here is something I do want to delete. Is this easier to delete? Why? It only has one child. So because it only has one child, deletion means promote the child instead of. So there is two aspects here. Find a successor, that's in here. Part number two is realizing by that swapping those things, it's still a binary search tree. It's a different tree, but I didn't change the left node value property. Now this one I don't want to delete anymore because this is the value that was here. This is the one that I want to delete now, which is much easier to delete because it only has one child. This is not a hard operation if you work with pointers, it's really like 6 lines of code. But if you just learn pointers or if you don't learn pointers, it gets messy. So I'm totally okay if you don't submit demo this part. Okay? So if you feel like after do everything but deletion, you kind of fed up with binary search trees, okay, leave it for algorithms because it's gonna come back to you for sure. Okay, that is what I wanted to say about a lot of things. Just I have to show you recurrency so you can do the homework. So we're going to talk about recurrences more, but for now we have to figure out what to do with this homework. More being on Tuesday. So I did show you at recitation something about recurrences. Actually, let's put some recurrences in here so we know what we're talking about. Recurrences. Anybody remember binary search recurrence? To search in an array of size n, what do we have to do? Because a recursive call is going to be a recursive runtime. What is it?
2 times 2.
Binary search would go on both sides or just one side? Just one side. So it will be like this, plus 1. 1 to do the, find the middle of the array, and this is the side it goes. Ends up with remembers binary search. I check the middle, if it's there, good. If not, I go to either left or right. This is a problem, half of the array. That's binary search. How about merge sort? Merge sort. What does it do? It does the 2 halves. It sorts the half and the half, so that is 2t of n by 2. This is a different t. Every time you see this t in recurrences, it's a runtime of some algorithm, but this is the t for merge sort, and this is the t for binary search. They're not the same function. I just call it t as a problem. Here's the recurrence, but this is not the same t. And then merge sort does what? After it sorts the 2 halves, interleave them. That's n. That's merge sort. Okay. How about that one with another board here? Write it up here to be close to this binary search. You remember the problem with binary search modified? That was a nearly sorted array. What was that recurrence? I think we talked about that at recitation after the homework. Was t of n plus d plus 1. Was like binary search. You have to compare, but when you go to either the left side or the right side, you have to take a little bit more from the other side, remember? This is the array, and this is the middle of the array. But when we decided to go on one side, we have to take plus D from the other side, because the value we're looking for, if I compare my value, it's bigger than A of M. I need to go on the right side for the search, but I can't just go from middle to the right side. I have to include D values just in case the value might be there. So because I include those D values, now the recurrence becomes time to do this modified binary search. It's constant time to find the middle. But now the search space for the sub-problem, what I'm going into is not half. It's half plus D spots. So the effort will be T of N plus D, N by 2 plus D. Here's another few. I show you one that was complicated. I think was 4 T of N by 2 plus N. I think we did this at recitation as an exercise by induction, right? And we can add other things in here. You can have 4 T of N by 2 plus N squared. It really depends on different algorithms. This will be take few halves of the size of the array, 4 of them, execute the procedure on those 4 halves, and then the combination putting together part, it's N squared, like a table, like I have to write a table at the end. That will happen a lot in dynamic programming, where what you have to output, get the results, and fill a table, and by N of those results, like kind of board problems. These are recurrences, the runtime of algorithms. I want you to, from now on, the next week or so, and everything we do, I want you to think of recurrences, 2 problems from them. So the first one is already done, is how do you look at your algorithm, binary search or merge sort, and figure out the recurrence? Anybody knows quicksort? How does it work? Really quick. This not really a CS 1800 material. We going off the rails again. How does quicksort work? I'm looking to sort an array, right? Merge sort splits it in half, sorts the halves. What does quicksort do?
Quicksort finds a pivot point.
Find some index P in the array, and then
Turns everything around it, like around the pivot, kind of like a binary tree.
puts the right value here. This will be the correct value that it's supposed to be in that spot. And then
it like pivots everything around that right or left.
everything here, like if this is a value B, everything is more than B here, and everything is greater than B here. So quicksort does one, it says, find me an index P and rearrange the array so that the value at that index is the correct value. That's done. I'm not going to move it from there. And then all the values that are smaller than that value go on the left side of the array. And all the values greater than that value go on the right side. So that's magic, right? So that's part number 1. It's called partition. Find pivot. P, that's an index. A of P equal V in that spot is final. That value won't move. This V is going to remain there forever. Any other index, if I is smaller than P, A of I has to be smaller than the value, and any J bigger than, these are all the I's and J's, any J bigger than that, A of J have to be bigger than the value. So it didn't sort anything. It puts some value in the middle that's in the final spot, somehow, magic. And then it moves all the values bigger on the right side and all the values smaller on the left side, so it destroys the array in that operation. It says your original array is gone, here's your new one. I mean, it has the same values. It didn't sort them. This is not sorted. This is not sorted. It just puts a value in the middle. It says smaller or bigger. Ends up with me. Now, we don't know how it does this. It does it somehow, partition function. That's not a recursive call though. It just does some thingies in between. But now, what can I do now to move forward? Assuming this is done, what should I do now?
You can call quicksort on the i's and then call it again on the j's.
Right, on the left side, you say i's, right? And then part 3 is called quicksort on the right, which is the j's, right? The principle being, now all I have to sort is this and that, and the whole thing will be sorted. Right? If this is in the correct spot B, and those are all the smaller values, if I sort those, and then I look at B, and I sort the right side, independently of each other, I can call these two computers in the same time, right? Once I did the partition, I can send this to some server, send this to another server, and independently they can be sorted. They don't depend on each other anymore, because this V is permanently set in stone here. What's the runtime of this? If I am to think recursively like I did on merge sort, the runtime for quicksort, it's gonna be the runtime of partition, however it takes to do this organization, plus how big is this side here? Is that half of the array? Not necessarily. I think that's like T of P, however big P was. And how much is the other side? N minus P. So if P is, in the middle, that's half and half. But if P is like a quarter in, that's a quarter and that's 3/4. And partition doesn't guarantee P is going to be in the middle. That would be nice, but it does not. Yes?
Will not be n minus p minus 1.
Yes, I'm skipping that detail. Correct. So this runtime, it's a function of where those pivots end up being. It'd be nice to be always in the middle. If it be in the middle, I'll have almost the merge sort time, right? But I mean, I don't know what is this data of. So that's an exercise for you guys. Forget about quicksort. How fast can you do this? Find something, put it in the final position, move the left values to the left and the right values to the right in an array. How fast can one do this?
2 questions. Where do you account for finding the pivot itself?
That's part of the partition.
That's part of the partition.
So that finds the pivot. Find pivot. It's part of the partition function. That's not, again, that's not a recursive call. It's like in merge sort, that's the interleaving part. So how fast can somebody do this? Find me a pivot, put a value that's correct, small values left, right values to the right. Yes? Linear. Anybody else? Maybe linear at this point. Yes? Usually it's random. So usually the value, which is the value at the pivot, is random. That's for controlling, on average, the split. So the good idea is to pick a value at random for the pivot. Don't pick the first one or the last one. Now, we're going to talk about quicksort later as an algorithm. What I want you to see is how recursive runtimes come out of these algorithms. If you do that, it's a T of n, it's some theta of n, plus now I have this pivot, I have to average over all the possible pivots if I want the average time. What if I want the worst time? What would be the worst pivot one can find? Right. Every time the pivot ends up being in here or in here, it kind of only solves a little bit of a problem and you still have to deal with n minus 1 values. That's no good. So the worst case will be T of n is n plus T of 1 plus T of n minus 1 like this. Now do we know how to solve that recurrence? T of 1 is a constant. It's not part of the recurrence. It's really a constant plus T of n minus 1. So it's n plus T of n minus 1. That will be n squared. It's a very similar way with insertion sort in that case. So many algorithms that you're going to study, in fact, all of them, have this behavior of a recursive runtime. How about, here's a simple one. How about max? But max recursively. I think of max as being max in an array A. It's either A of 1, the first one, or the maximum between A from 2 to n, the other values. So it's like, check if it's the first one somehow, between the first one and the rest. So that max will say, find the max in the remaining of the array, and then compare that max to the first value. And if the first value is bigger, that's the max. If the maximum in the rest of the array is the maximum, that's the one. Would that be the correct max? So how do I implement that as a procedure? I call V is the maximum recursive call of A between 2 and n. And then I say if V is bigger than A of 1, return V. Else, return A of 1. Is that the correct max procedure? Look for the maximum in the rest of the array except for the first one. Then compare with the first one. If the first one is bigger, that's your max. If not, the rest is the max. What's the recursive runtime for this? To do this, I have to find the maximum in the rest of the array. How long would that take? N minus 1. And then how long does it take to compare that with the first element? 1. That's another runtime that if you want to implement max recursively is this runtime. So now that we understand where these recursions come from, there's two things with that. One is to guess what they are. What is this? This is theta of what? Good guess. How about this one? Guess. I'm not confirming or infirming anything. I'm just saying, he says that, I write it on the board. How about this one here? This one I guessed at the recitation, no? But I couldn't prove it. You guys remember that I guessed something for this one, but I tried, one proof worked, the lower bound, and the upper bound didn't. What was my guess? Remember that I could prove n cube as an upper bound, but not n squared? I stand by my guess. No. How about merge sort? Do you have a guess? How about binary search? How about this modified binary search? Log n. So the fun part of recursive functions is the guessing part. What is it? Right? And you can be right or you can be wrong. Now, after you guess it, we can do inductive proofs. That's what I was starting with this problem at the Wednesday and Thursday at recitation. I was showing if I have a guess, I can attempt an inductive proof of that. In fact, let's do one really quick here to practice a little bit of induction. I'm going to take a merge sort. T of n is 2t of n by 2 plus n. Is that right? That's the merge sort. Now my guess, I already have the guess, n log n. I want to prove this by induction. Looking at the recurrence, what is going to be the induction step here? From where to where? So induction step is going to be from who to who? N by 2 to n, right? Because it's depending on n by 2. My new customer, it's a function of the old customer, which is not n minus 1, it's n by 2. So now what's my induction step? If t of n by 2 is between c2 n by 2 log of n by 2, right? And bigger than c1 n by 2 log of n by 2, that's the hypothesis. The property is true for n by 2. Then it's true for n. C1 n log n is smaller than T of n, smaller than C2 n log n. What am I doing here? I'm doing the same thing I tried to do at recitation and failed, because I can only do the lower bound. I did half, but I couldn't do the upper bound. That proof didn't work out, right? I'm trying to do the same thing here for a different recurrence. And since it's a theta bound, it's left and right. But O bound will be just the right side. The omega bound will be just the left side. This is the left bound, lower bound. This is the upper bound. Again, this is the lower bound. This is the upper bound. If you can do both, you do just one side. The left side is omega, right side is theta. But we're trying to do both. So let's do a proof for the lower bound. My new customer, T of n. Who is the new customer in a relationship with all customers? All induction proofs were like this. Who's that? T2 of n by 2 plus n, right here. The relationship between T of n and T of n by 2 is this one. It's always the recursive equation. That's why I choose this induction step, so I can relate the new customer to the old customer. If I choose a different induction step, I wouldn't be able to do this. So now, can I use the induction hypothesis? Remember, I'm trying to prove the lower bound. So I'm trying to prove that this guy is bigger than something. To prove the lower, I'm going to use the induction hypothesis on T of n by 2 to do something here. So T of n by 2 is bigger than what? C1 n over 2 log of n over 2, right? It's an induction hypothesis, right? Plus, I still have this n. Now, if I open parentheses, what is this? 2 goes away with the 2. So I get C1 log of, it's an n in there, n by 2 plus n. And log of n by 2, can I think of it as a difference? Log of n by 2 is log of n minus log of 2. So that is C1n log n minus C1n log 2 is how much? All the logs are binary logs in here. That's 1 log of 2 plus n. Is this wishful thinking so far? This bigger than, equal than are things that I know or I'm trying to prove. How did I get from here to here? This inequality comes from where? Induction hypothesis. I know that. How do I get from here to here? I just simplified the fraction. How do I get from here to here? I expanded the log into log of n minus log of 2, right? That's what this log n is. So that I know. Now comes the what I want. What do I want? For this T of n, what is my ultimate purpose for the lower bound? To prove that it's bigger than what? C1n log n. That's what I want. I want the T of n to be bigger than this. Hands up who's with me. Now let's play our game with manipulate both sides. That looks good right here, right? Out. So what am I left with? N has to be bigger than C1n, right? Because this n moves on the right side. C1n moves on the other side. That's the same as saying C1 has to be smaller than 1. So what this is saying, you can make this happen, your wish, if you choose a constant that's less than 1. So you can choose a constant like 0.8 or 0.5 or something that's less than 1. Because if you want this to happen, the constant has to be less than 1. Remember, I can choose the constants, but only once. What do you think is going to happen in the upper bound?
C2 has to be greater.
Exactly. 2 t of n by 2 plus n. That's going to be smaller than, this is an upper bound, so it's going to be 2 c2 n by 2 log of n by 2 plus n. That's going to be c2n log n minus c2n plus n, which we want to be smaller than c2n log n. That can happen if c2 is bigger than 1. I simplified a few steps. It's exactly the same derivation, but the inequality is backwards. So this is much better than we did at recitation. At recitation, the whole C1 went away with C1, and we ended up with n bigger than 0 or smaller than 0, that we couldn't make it work. But this one, it works if we set the constant C1 less than 1 and C2 more than 1. There are some additional restrictions to those constants via the base case. So when we do the base cases, which we're going to probably talk about on Tuesday, we'll see that this is not the only restriction that we have. But this clearly works. Okay, so that's a proof that if somebody tells me merge sort n log n, somebody said n log n, I could prove it, but this will be kind of hard if I didn't know what to prove, right? Like if I don't have the right guess here, I don't have to prove it. Let me do the same here for another one. Let's take the binary search. Binary search. What's the recurrence? T of n is T of n by 2 plus 1. And what's our guess? Data of log n. So what's the induction step here? How do we prove? The actual definition is T of n has to be between C2 log n and C1 log n. Who is going to imply this? The induction step. It's going to be from where to go, I go to n. Same principle. I have to be able to relate the new customer with the old customer, always. So before I write that, let's imagine how the proof is going to go. The proof is going to be T of n, that's the new customer, is equal to the old customer. So who's the old customer? Who? T of n over 2. So this has to be T of n over 2 is smaller than C2 log of n over 2, bigger than C1 log of 1 over 2. It's the same property, but for the half. Again, there's a lower bound here, and a lower bound, and there is an upper bound here, and an upper bound. That's because we in the other sections do both bounds. We call it theta. The regular section only does the upper bound. But they'll do it in the algorithms course anyway. Okay, so proof for the lower bound is going to be very similar with that one. T of n, what's the relationship between the new customer and the old customer? I want to prove a lower bound, so this has to be bigger than. What can I do about those T of n by 2 here? It's bigger than what? From induction hypothesis. I want to use the induction hypothesis to say this is bigger than something. What do I do?
C1 log. Oh,
Right? That's the induction hypothesis. This is bigger than that. Plus the 1. Now I do, log of n by 2 is log of n minus log of 2. So that C1 log of n minus C1 log of 2 is 1 plus 1. And now what do I want? This is all good up to here. I know that. But now, what do I want T of n to be bigger than? What am I trying to prove here?
C1 log n.
C1 log n, right? So now, I start playing that game, and I get what? 1 has to be bigger than C1. This is a set. That's a condition. Call it constraint. To be very mathematical. A constraint means you can choose any constant you want still, but it has to be less than 1. You can choose less than 1. Now all constants have to be positive. We don't do negative constants here. So for C1 to be valid, it has to be between 0 and 1. And you can do the proof for lower bound, for upper bound. That's going to be same relationship. It's going to result in C2 being what? Greater than 1. It's the same exact derivation with C1 instead of C2 and with the inequalities backwards. So that's how I prove already that this is theta of log n. I skipped the base cases because they are non-trivial. I want to do them on Tuesday. So we get back to what's the base case here. But you can see how if my guess was correct, log n, no question asked, how did I get log n? I asked him. That's how I got it, right? I could prove this by induction. And the proof, once it's done, it's done. This guy has to be theta of log n now. And no way to play around. The only problem is making a wrong guess, and then the proof doesn't work. And then you don't know if the proof doesn't work because you don't know how to do it, or because the guess was wrong. Let's have a question?
Yes, so let's say we give me making a guess, like a master theorem, and I want to use that on my finding, but you can't use that. Can I use that to get my guess and prove it by?
Yes. Okay. We'll talk about that on Tuesday, master theorem. But for now, how can I make a guess if I don't know master theorem? Finally, we get into solve recurrences. How can I make those guesses? If I don't know binary search exactly, or if I didn't think about it, and if I don't know master theorem, which we're gonna know for sure in the other section, how do I make those guesses? It's much easier than you think, but unfortunately it's tedious. So there's nothing complicated about those guesses. Just grinding until you can make a good guess. That's what it is. So what do I mean by grinding it? Well, let's take this one. How do I make a guess here? T of n is T of n by 2 plus 1, right? Now, because it is a recurrence, I can apply the same recurrence again for T of n by 2. That is a very important fact for recurrences, because this is for any n. So if I apply this recurrence, call it, you know, if you have a flower here, anything really, that's T of the flower that you have by 2 plus 1. So you can put anything you want in there, as long as on the other side you put that by half. So now what I want is to put T of n by 2. So if I open this, it's going to be T of, if I apply the same recurrence for T of n by 2, what do I get? N by 4 plus 1. Now this is just the T of n by 2 here, plus another 1, right? The 1, it's the one I had. This one comes from applying the recurrence. And that is T of n by 4 plus 2. Now I'm going to apply the recurrence again on this T of n by 4. I put square brackets to make it clear that what I'm replacing is the T of n by 4. If I apply the recurrence for T of n by 4, what do I get? T of n by 8 plus 1. And I still have a plus 2, because that's from before. And this is T of n by 8 plus 3, right? How many do you do? That depends how smart you are. If you're very smart, you figure out what it is. If not, you do a few more. It's just a matter of time. Let's do one more. Now this is T of n by 16 plus 1 plus the 3. So that's going to be T of n by 16 plus 4. So your purpose when you decide, okay, I've had enough, I know what it is to do a generic K after K iterations. So there's 1, 2, 3, 4. What happens for a generic K? This would be T of, I'm looking at these guys. Can you find out the pattern? Is there a pattern here with each iteration? If this is, let's call this here K equal 2, K equal 3, K equal 4. Can you come up with a general formula for K? What is it? Just looking at those results. You don't want to look at the kitchen mess part, just at the right side. What is the general formula?
C of n by C of k.
Everybody sees that? That this is a pattern that keeps repeating. Again, how many times you repeat it, that depends when you start figuring it out. And once you find this pattern, the rest you have to do like I'm doing it here. You have to figure out what is your last K. Last K means this is a generic step. K equal 3, 4, 5, 6, 7, 8, so on and so forth. When this becomes base case, how big K needs to be so that this T becomes either T of 0 or T of 1 or something basic? So how many steps do I do until I reach the base? That's the question. Here's how to think about that. What I want is the inside there, T n2 to the K, to be about 1. Because that would be my base case, T of 1. So that's equivalent. What K do I need so that n divided by 2 to the K is about 1? K is log base 2 of n. So I keep going with these steps. Well, in the last K, if I replace K with that value that I just got this way, if I figure out the base, this is still going to be T of n, the original one, is going to be T of n divided by 2 to the log base 2 of n. Of course, that's 1, because that's how I set it up. Plus K is log base 2 of n. So this is T of 1 plus log base 2 of n. T of 1 is a constant. So this is theta of that's how we solve recurrences. We push them and push them and push them until we find a pattern, and then we figure out from that pattern what it is. In the event that the derivation gets super messy, like we can, this is clean, this is a full credit sort of clean mathematics, but if it gets messy, instead of totally abandon it, sometimes what we do, we still make a guess. Remember, we only need a guess, and then we prove it by induction. Maybe I couldn't get it clean to be theta of log n, but if I kind of look at it and say, aha, I have an idea, I don't know how to finish this, but it's log n, I could go back and do the proof by induction. So this could be either a complete solution, or it could be just a guess. How about that one in there? Can we do the same here? How did we get this guess? Theta and log n, right? Let's see. T of n is 2 T of n by 2 plus n. That's merge sort. What happens if I push this? Again, I'm going to put square brackets just to indicate that I'm applying the recursion to T. The rest of it will be the same. 2 times that plus n. If I apply the recursion to T of n by 2 here, what do I get? Plus, how is the flower looking here? If I want my flower, that's 2 times the flower by 2 plus, not plus 1,
Flower.
plus the flower. So if I apply this on T of n by 2, what comes here? What's the flower here?
I don't know.
Now, you ever, so typically in business, the tick-tock approach, tick step, do something, tock step, do something else, and can repeat that. That's exactly what you want to do with the algebra here. You don't want to move to the next iteration until you clean this up. Because if you do, your life will become harder. One step is keep iterating. The other step is clean it up. So how do we clean this up? We do some 2 by 2 is that's 4 T of n by 4, right? Plus 2 times n by 2 is n, plus another n. That is now 4t of n by 4 plus 2n. That's the cleaning up. Now we can apply the recurrence again. So now I have a 4, is 4 in here. My square bracket, which means I'm applying the recurrence to the t. So now I have the flower is n by 4. What is this going to be?
2 n by 8
Plus n by?
4.
Gotta get fluent with those flowers, right? The flower here is n by 4. Plus I still have the 2n. A very common mistake for people who just start recurrences is to forget about this stuff. I expand the recurrence, but I totally forgot the 2n. Minimum half of the mistakes in this class with the recurrences are for people forgetting about this 2n here. They just stop after 4 of that. That's it. Clearly I had a 2n. That's why I put those square brackets. To be visually clear, this is where the expansion, the iteration happened. The rest of it stays the same as in previous line. Now cleaning it up, the talk step, this is 8 p of n by 8 plus, let's do this quick, 4 times n over 4, that's 1n plus 2 more n's. Are we smart enough to find the pattern here, or are we doing more? Do we know the pattern? What is for a generic k, the pattern? How this dude gonna look like for a k? This was k equal 2. This is k equal 3. How do you think it's gonna look in general? 2 to the k, t of again, how many, there's no shame in doing iterations. It's much better to do more iterations and get it right than to do fewer iterations and get it wrong, right? So if you're not sure, do 1 or 2 or 3 more iterations until you're sure that you find the right pattern. Now, once you do, what is the last k? Again, we need the interior of t to be a base case. So n divided by 2 to the k is about 1. That line before k is about log n. So then means t of n, it's 2 to log n times t of 1 plus log n times n. So now, how much is 2 at log n? N times t of 1 is a constant plus n log n. So this is theta of, this is n, this is n log n. Which one is bigger? N log n. This is how we solve recurrences. Again, if this is clean, like in here, this counts as clean. We can leave it at that. But if it's messy and we couldn't really do what we need in here, then we have to just make a guess and go back and prove it by induction. Let's do one more. Maybe 2 more. Let's do that one that we couldn't do at recitation, remember? There was one, this one was the one that we didn't work out at recitation. We say it's n squared, but when we try to do the proof by induction, we can only do the lower bound. Let's see, maybe it comes out nicely as n squared, so we don't need the proof by induction, so I'm off the hook next Wednesday and Thursday. Please expand. 4. What's the flower here? This t gets expanded right here. What is it? If I apply the recurrence in t of n by 2. So there's the same recurrence, but my flower is going to be n by 2 now. What do I get? 4t of n by 4 plus this n becomes n by 2. Remember to clean it up. This is a 4 squared, 4 times 4, t of n by 4, plus how many n's are here? 4 n by 2, that's how many? 2n plus n is 3n. So now I'm expanding again, 4 square bracket, because I'm only expanding the t plus 3n. What is now t expanded next iteration? 4t of n by 8 plus n over 4. Hands up, who's with me? I'm applying the same relation to n by 4 now. So now, this is 4 cubed t to n to the 8 plus, how many n's are in here? 4n. 4n plus 3n. Let me give you a small trick in here. The talk step, it's not necessarily useful to be very concise. The best thing, your objective for this cleaning up step is to make it most visible. Because you remember, you want to try to guess that pattern, the more visible it is. So I don't know about the 7n. How about 1n plus 2n, would that be easier? And then 1n plus 2n from before plus 4n. Maybe that will, it's the same, just maybe it'll be easier to see. Let's do it one more time. So 4 cubed, that one, square bracket, that indicates I'm going to expand this guy. So this will be 4 to the n by 16 plus n to the 8, right? Plus, I still have these n's, 1n plus 2n's plus 4n. Now what do I get? 4 to the 4, t of n to the 16. Now how many n's are here? How many n's are 4 cubed multiplied with n by 8? How many? 8? So at 1n plus 2n plus 4n plus 8n. That starts looking good because it looks like a pattern. Every time you see a pattern here, you should be happy because it means you're going to have an easy time guessing it. What's the general k? So let's call this k equal 4. And this is k equal 3. So for a general k, what is this going to be? 4 to the k, t of
N over 2.
to the k. Plus n, that's an n common factor, right? 1 plus 2 plus 4 plus 8 plus, let's write it nicer, 2 to the 2, 2 to the 3, all the way to 2. What's the last power? Is it k? K minus 1. Yeah. Are we seeing this? It's totally fine to do more iterations before you can see a clear pattern. Now, before I move to the last k, I'm going to apply the geometric series here to simplify it a little bit. So how much is this? 4 to the k of n 2 to the k plus n times, this is 2 to the k minus 1 divided by 2 minus 1. So the last k is who? It's going to be log base 2 of n like before, because I want the interior of t to be 1, to be a base case. I want n to 2 to the k to be about 1. So then if I replace this k inside there, what do I get? 4 to log base 2 of n times t to the 1. That was by design, so I get 1 inside the t. Plus n times, how much is this? 2 minus 1 is 1. So I get 2 at log base 2 of n minus 1. I think I showed you guys that 4 at log base 2 of n is the same as n squared. Do you remember that? Because I can do n at log base 2 of 4. I can switch the n with the 4, and log base 2 of 4 is 2. So this is n squared t of 1, plus how much is this stuff in here? N squared minus n, right? Because this is just n. 2 at log n is n. So n times n minus 1 is this. Now in terms of a data bound, what is this? N squared times a constant plus n squared minus n. So my guess was right. at recitation with this problem. Just I couldn't do the induction proof. Anybody did that induction
that
proof,
infinite
the upper bound,
Whatever n.
by induction?
Yeah. There's not really an
No. Here's, I'm not gonna do one more because we're done. But what's gonna happen when I do T of n is T of n by 2 plus D plus 1. Let's expand this guy just one time. Huh? One time. What's gonna happen here? When I expand, this is my flower now. So how do I expand that? If I apply the recurrence, my flower is n by 2 plus d. It's gonna be n by 2 plus d half plus d, right? Because it gets a d plus 2. Now remember we have to clean it up? Because after you expand, you always clean out. 2 of, what's the story here? It's n by n plus d plus 2d by 4 plus 2. So it's easy to see that if you expand it again, which I'm not going to do, you get n plus d plus 2d plus 4d by 8 plus 3. So you keep expanding it until you figure out what the pattern is, and then you can tell whether this is what asymptotic function.
I was reading this
Who wants to play? Oh, I'm gonna go Flash. I really don't care. It would take a stupid amount of effort for me to fail that class at this point. I'm here, you're like up here right now.
Single callback yet.